Okay. So once you answer that question, you go through this other kind of joined topic, but different, I guess. So when we want to determine whether it is getting warmer or cooler over a period of time, we analyze data for trends. So this figure right here shows the average June high temperatures that has been plotted for the Pullman Airport all the way from 1940 to 2019. So that is the purple line that you're seeing. As you're seeing, some years they didn't have data for, so there's a couple gaps. The red line that is over here is, and a straight line that is dashed, is the trend line that shows the trend for that data. So overall, it's kind of like averaging it out in a way and seeing what is overall happening. So you might have seen those kind of lines before. So the trend line kind of tells you, is it increasing, is it decreasing, and to what degree is it doing it? And you might have used this formula before. So this is y/mx plus b, so we'll go through it. So on average, are Pullman June temperatures increasing, decreasing, or staying the same? So on average, so meaning based on the trend line, what are they doing? Temperatures are here on the y-axis, and years are here on the x-axis, so you tell me. Okay, so now, remember the basic equation for a line is y is equal to mx plus b. The slope of the line is m, so that is the slope. The y-axis intercept is b, so that is where on b does this go. So for example, the b or the y-intercept or b is 70.762, which is about this point, which makes sense. That is the y-intercept for this data. And then the slope of the line indicates the change in y values over x values. So how much are the y values changing over the x values changing themselves? What is the change that you're seeing, basically? The y-intercept indicates the value of y, yes, and the y at the y-axis where x is 0. And the equation of the trend line in this graph is, so in this case, clarifying this, when x is 0, this case we are considering 1940, the year 1940, to be x equals 0, okay? Because that is the first year that we have data for. Okay, so the equation of the trend line in this graph is equal to y equals 0.0168, so that would be equal to mx plus b, or 70.762. So using the slope, which is again this bit of information, you can calculate the modeled average number of degrees warmer in June 2009, comparing it to June of 1941. So calculate the increase in temperatures for June 2009. So here you would input the degrees per year, so that would be the slope, right? So you would pretty much just put this. And then you would multiply that times the number of years of data. So if you are trying to calculate June of 2009, you know that you had how many years between 1941 and 2009. So I'll let you input the number of years over here. And that will give you a value for x, which is equal to the degrees warmer in June of 2009. Okay, good. So this type of calculation is a simple climate model. Climate models allow us to predict what climate would be like. We can use the entire equation to predict what the high temperature might be like. So now I'm asking you to calculate the model prediction for high temperatures in June of 2010. So you gotta input the slope again over here, times the number of years of data. In this case, 2010, not 2009. And so this is gonna be slightly different. And then in this case, you are adding the b number or the y-intercept to that, and then you'll have a predicted temperature for June of 2009 based on the previous data. Okay? And now, the actual average of June high temperature in Pullman 2010 was of 67 degrees Fahrenheit. So is that more or less than the predicted average? And by the predicted average, they mean the number that you got here in number 9. Alright, so based on that, you'll be able to answer the last few questions from part 1 relatively easily. So I'm going to go ahead and skip through those. Again, on your quiz online, you have multiple choice for all of them, so that's convenient. But try to complete the lab before you start the quiz, okay? Because it is timed and you won't have enough time to complete it on your own before you run out of time. Okay, so let's go back to the lab. All right, so part 2 is called Reconstructing Climate with Proxy Records. So in the first part of the lab, you calculated a climate normal from observations made at weather stations. In trying to reconstruct historic climate, we don't have observations for most locations prior to the 1900s, which makes sense because back then we didn't have basically thermometers in order to check what the temperatures were at any one location. So in order to calculate those temperatures, we have proxy data. So proxy data is a substitute that recorded the weather conditions in some other fashion. And as we have seen in lecture, some of that proxy data can be things like tree rings, coral rings, ice cores. All of those are good proxy data that we use. For example, well, the word, I'm blanking on my word, but palynology too, as you have seen again in lecture. So one of the best proxy records available in climatology are tree rings. The growth is dependent upon temperature and precipitation. So tree rings are wider or narrower depending upon the conditions for a given year. So if, for example, that specific ring is relatively wide compared to other ones, it means that the conditions were good. They were prone for growth of that year, of that tree. So perhaps if that specific type of tree needs a lot of water and a lot of heat, because it's in the tropic, let's assume, then the fact that it's wide means that that year got a lot of water and a lot of heat. If, on the other hand, it's very, very thin, it's possible that that was a dry and a cold year. Okay, so it's a proxy data. It doesn't tell us exactly how much it was, but it gives us an idea of overall what was the environment like at that point. So, since trees only normally add one ring per year, we can easily date trees to link the climate conditions to the year they occurred. So it's very convenient. We can measure each ring and we can measure how wide it is. So we can sort of give a condition to that specific year based on how wide the ring is. Okay, so this is how they do it. So they would take pretty much a slice from the center of the ring or the core of the tree all the way to the edge, and that would be the particular core tree ring that they're examining. Okay. So another climate proxy often used is an ice core, and you'll see that later. These cores, drilled thousands of meters into the ice caps of Greenland and Antarctica, give climatologists a different and much longer scale view of how climate has changed and how the atmosphere has changed over time as well. You'll explore some ice core sites in part 3 of this lab, so that we'll leave for a little bit later, but again, it's another good data proxy that we have. Okay, so in most of the western United States, tree ring width is indicative of whether it was a wetter than normal year or a drier than normal year, or a precipitation normal year. In the example below, 5 rings are highlighted. So if this were to be, for example, the ring they took from here, this is what it would be if it was zoomed in. Okay, so for each ring, use your ruler to measure the width of the ring in millimeters. So for this, you need to make sure that you are at a 175% scale at the bottom of the page. So right now, as you're seeing, I am at 100%, but if I want to get the right measurements according to what the answer is, I want to be at 175. So you want to do that yourself if you're going to do this lab right. So this is the scale at which you have to be in order to record the widths of each of these rings. Okay, so first you record the widths of each of these rings that is highlighted onto the table that is here below. So don't worry about writing whether it's wet, dry, or normal yet. just record the widths in millimeters. Okay, so for example, if I were to do that with 1, I would measure it. You can't see what I'm doing with my hand, but I would measure it and assume that I have 20 millimeters, so I would write 20 millimeters. As you can see, rings 1 and 2 are thicker than number 3. Ring 4 is almost as thick as 1 and 2, and ring 5 is perhaps close to number 3, maybe a tiny bit thicker. So you record those millimeters that you measured for each of those rings onto the table. All right, so in some places where there have been weather stations for several decades, we can use tree ring data with weather station observations to determine the relationship between tree ring width and actual observed precipitation. On the graph below, a relationship between precipitation and tree ring width has been plotted using known weather observations and tree rings for this location. So that would be this data right here. Now it says, locate the measured width for each of your 5 rings to determine that the precipitation was for the associated ring. Determine if each of the 5 rings was either wet, dry, or normal years. Okay, so as you can see, this data here is kind of split into 3. Normal years would be somewhere in between where the tree ring width is somewhere in between 6 and 11. So how am I doing that? You see that normal years would be in this range. So wherever my line intersects the 2 lines that divide normal years from wet and dry years. So as you can see, the tree ring width here on the x-axis, it's about 6 when it becomes normal years, and it's about 11 when it starts getting into wet years. So if I have a tree ring width between 6 millimeters and 11, that means it's normal years, normal precipitation. If my tree ring width is below 6 millimeters, so if it's only 2 or 3 millimeters in width, that means that that year was dry. If my width of the ring is greater than 11 millimeters, then it means that that year was particularly wet. Okay? So don't worry about these data points that they have here. They were just used to, again, make the line based on the location where they had both temperature observations and tree ring widths. So don't worry about it. They're not your data, nor do you have to deal with them right now. You just have to deal with this line and the specific classifications for the dry, normal, or wet years. So once you have recorded whether your ring millimeter was corresponding to wet, dry, or normal, then you check for the precipitation that corresponds to it. So, for example, if I had said that my first ring was 20 millimeters, let's just go with that. 20 millimeters is clearly beyond what I have over here, so it's definitely on the wet years. Okay, let's assume that if I continue this relatively straight, 20 years is probably over here, and if it was over here and I take this across, the number of inches that it rained during the year was probably close to, what, 40 inches based on the scale that they have. So then I would record, again, 20 for the millimeters width. I would record that this was wet, and I would record 40 inches of precipitation. So all of these ring measurements should be within this table, so that will help you out a little bit. None of them should go beyond 30 or below 0, I guess, precipitation. So that should help also make sure that you're in the right measurement scale. When you are doing this, especially the measuring of the rings, don't get too stressed out based on the answers. So in the quiz, the answers are very far apart from one another. So I'll show you. You can see that each of these answers is well apart from one another. It's not like I have 1, 2, and 3 as possibilities, but rather I have something that is very far away. So if you don't measure, like if you measure, for example, that it was 3 instead of 2, the closest answer would be 2, so you would choose 2 instead. Okay? Okay. All right, so that's where you're going to record on your table. Then you go on to the questions. So